What if I told you that you use this incredibly powerful problem-solving skill every single day, and you probably don't even realize it? I'm serious. From making your morning coffee to figuring out the quickest way to get somewhere, you're constantly structuring solutions. Today, we're going to pull back the curtain on that very skill, algorithmic thinking.
So here's our roadmap for this explainer. First, we'll nail down what an algorithm actually is. Then, we'll look at the rules every algorithm has to follow. After that, we'll see how to draw them out with flowcharts. And finally, we'll get into the two basic ways they work, in a straight line and when they have to make a choice. Let's do this.
All right, let's just dive right into the deep end. I mean, really think about it for a second. How do we solve any problem? We follow steps, right? Whether you're trying to navigate to a new restaurant or putting together some IKEA furniture, you're breaking a big challenge down into a logical sequence of smaller actions, often without even thinking about it. Let's take making a frappe, for example. It's just a simple recipe, but look a little closer. It's a list of super clear ordered instructions. You follow them one by one, and if you do it right, you get a perfect coffee every single time. The order is crucial, and each step is a totally separate action. And, you guessed it, that simple recipe you just looked at? That's a perfect, real-world example of an algorithm. See? It's not some scary, complex idea that only computer scientists can understand. It's something you literally use all the time.
And here's the official textbook definition. Yeah, it sounds a little technical, but just think back to our frappe recipe. It fits perfectly. It's a finite series of clear, simple, effective steps. That is the heart of it, whether you're making coffee or telling a computer how to sort a billion pieces of data.
Now, not just any old list of instructions gets to be called an algorithm. To earn that title, a set of steps has to play by 3 really important rules. And these rules are totally non-negotiable. First, an algorithm has to be finite. It has to stop eventually. Otherwise, it's just a useless, infinite loop. Second, it has to be effective, meaning each step has to be something you can actually do. Invent a time machine is not an effective step. And finally, it has to be well-defined. There can't be any confusion. An instruction like, add a bit of sugar would fail, because, well, how much is a bit? Okay, so words are great, but sometimes a picture, a map, is so much better. And to visualize the logic of an algorithm, we use this really cool and powerful tool called a flowchart.
Just think of it like a roadmap for your instructions. It uses a set of standard shapes, all connected by arrows, to show you the logical flow of your process, from the very beginning all the way to the very end. It just makes the whole thing easy to see at a glance.
These shapes are kind of like a universal language for logic. You've got ovals for the start and end points, parallelograms for when you're getting information in or putting it out, rectangles for when you're actually doing something. But pay close attention to that diamond. That's the decision maker, that's the crossroads, and that is where algorithms get really interesting.
The most basic kind of algorithm, just like our coffee recipe, follows what we call a sequential structure. The steps are just run in a straight line, one after another, no questions asked, no detours.
So let's take a super simple problem that fits this perfectly. Calculating the perimeter of a square. We're given the length of one side, and all we have to do is find the total distance around the outside.
And here's exactly what that looks like as a flowchart. See how the path is just a straight line down? We start, we get the side length, we do the math, we show the answer, and we end. That's it. There are no choices, no detours, just one step right after another.
But life is almost never a straight line, is it? So what happens when our problem actually requires a choice? This is where that simple, one-track mind of a sequential structure just isn't enough, and we need something a bit more powerful, a branching structure.
So how do algorithms handle making decisions? This is where they start to feel kind of smart, choosing to go down different paths based on the situation they find themselves in.
Let's imagine this real-world scenario. The logic isn't always give a discount. The logic is give a discount if a certain condition is met. The algorithm has to ask a question before it can figure out the final price. And this right here is that crossroads we talked about. It's that diamond shape. The entire flow of the algorithm now depends on the answer to this one simple yes or no question. This single point decides which path we're going to take next.
So, let's say a customer spends 120 euros. We hit the diamond, the answer to our question is yes, so we follow the path that calculates a 10% discount. But what if the next customer only spends 80 euros? Well, now the answer is no, and the algorithm takes the other path where the discount is 0.
And notice how both paths eventually merge back together at the end to calculate the final price. That's branching in action. It's pretty cool. And when you boil it all down, this is what algorithmic thinking is really about. It's not just for programmers coding on a computer. It's a powerful framework for anyone to solve problems in a logical way, making sure you've thought through all the steps and all the possibilities.
So I'll leave you with this question. What everyday process in your life could you map out as an algorithm? Your morning routine, how you decide what you're going to have for dinner? The real power here isn't just knowing what an algorithm is. It's realizing that you can actually start designing them on purpose to make better, more logical decisions about almost anything.